Hello, my name is Gerald and I'm with the company Lucas-Nülle. Today I would like to speak about our training systems for electric machines, drives and power electronics. Here you can see a typical workstation for these topics. In the upper row you see our line-commutated power converter circuits. Below here are the self-commutated power converter circuits with IGBTs. And in the middle row is our control unit for the dynamic servo machine test stand. I'm going to focus only on the servo machine test stand with our electric machines and the line-commutated power converters. The beauty of our system, of all our panel system, is that the panels are completely modular. That means you can easily remove and remove these panels. All of the panels are made out of a synthetic resin bounded material. That means this material is non-conducting and it's not flammable. I'm gonna remove this panel here. Okay. In this row you will see, as I told you, the dynamic servo machine test stand control unit. On the left side we have a multifunctional analog and digital multimeter. On this side we have a three-phase isolating transformer. Here we have our self-commutated power converter, and here is an intelligent power electronics load unit. On the tabletop you will see our servo asynchronous motor. The servo asynchronous motor has a built-in resolver with 64,000 increments per revolution. The motor here, which is called the MUT, the motor under test, is a three-phase asynchronous motor, squirrel cage. As you can see, this servo brake, we call it also servo brake, is connected to the control unit, and we can easily connect different kinds of motors to this servo brake. In this case, as I told you, we have a three-phase asynchronous motor, but this could be also an AC machine, a DC machine, a synchronous motor. And the way you couple these units is with this rubber coupling here. It's pretty easy to connect. That means you just connect these units to the brake unit, screw it down. Then we have a coupling guard. You connect this coupling guard on top of this, which also brings me right now to the safety features, which are really important. All our machines, doesn't matter whether it's an AC, a DC or a three-phase synchronous machine, have a built-in temperature contact. This built-in temperature contact protects the machine in case a student will, for example, break the machine down to standstill, and then they leave the room to have a coffee, and the machine is fully under load and it's getting hotter and hotter and hotter. So how do we protect this? The machine has to be connected to the servo machine test system controller, and already you saw in the display that now everything is okay. If I remove the cable, you see that there's an error message. That means you can't even start the system without connecting the temperature contact of the machine. I'm going to show you what happens if I start the brake, for example. I put some speed on it. Right now I'm driving the motor. So if the temperature contact released, I will simulate that. You will see that the control unit will shut down the whole system. The same thing will happen. I will start it again. The same thing will happen in case a student removed the coupling guard. The system will shut off and no dangerous situation can occur. Okay, I'm gonna put that thing back. Okay, so the multifunctional analog digital multimeter is used to display the different voltages, currents and powers. As you can see, I can show by pressing this button the voltage, I can show the current, I can show the active power, I can show the apparent power, the reactive power and the cosinus phi. Simultaneously, I can display 4 values, and I can even display these values in a digital way or in an analog way. You see, I can change between digital and analog. Yeah. In this case, I'm going just to display the voltage, the current, the active power and the cosinus phi. Right now, I'd like to show you how to use the servo machine test stand in a complete manual way. That means without any PC connection. Now I have connected the workstation to be used in a full manual mode. On the left side, you will see the power supply, which includes a motor protection switch. We have the 3-phase line power. The 3-phase line power goes into the control unit of the dynamic servo machine test stand, and from the control unit to the motor. In one phase, we have integrated the analog digital multimeter in order to measure the current and the voltage of one winding. Now I'm going to switch on the motor with this motor protection switch. That means the motor is now directly connected to the line power. This motor is a 3-phase asynchronous squirrel cage motor, and as you can see here, the motor runs with almost synchronous speed. As we are in Europe, the synchronous speed is 1500 RPM. In North America, the synchronous speed would be 1800 RPM. On the multimeter, you can see that we have our European voltage and currents. Of course, in the North America, it would be 120 volts per phase and 208 volts 3-phase. Now I'm going to use the control unit. The control unit can work in different modes. First of all, we have the torque control. Second, we have the speed control. Then we have a synchronization mode and a PC mode. About the PC mode I will speak a little bit later. I'm going to start the brake or the servo machine test stand by pressing the run button. And as you can see, this servo motor synchronizes exactly to the same speed of the motor under test, which runs in synchronous speed. That means it has no effect on the speed of the motor. By turning this knob, I can break down the motor. That means your student can reach every single working point in the characteristics of the motor and take their manual measurements. I can even break down the motor to stand still, and therefore we have this temperature contact here. That means if the motor will reach a critical temperature, the temperature contact will release and the motor can run again in idle or synchronous speed. Here you can see these indicators. We can display all 4 quadrants. Right now, if I go below the synchronous speed, you see that I'm running the motor clockwise in the motor mode. If I drive the machine, I can even drive the machine. You can see that I'm running the motor clockwise in the generator mode. Or I can even break down the motor and run it in the counterclockwise. Now the motor is running counterclockwise, as you can see here on this LED. Okay, now we are in the PC mode. I'm going to show you how we can work with our equipment using a PC. As you can see, the system is connected via USB to the PC, and the software that we are using is called LabSoft. LabSoft is our delivery platform for all our curriculum and contents. In this case, we work with so-called ILA courses. ILA stands for Interactive Lab Assistant. On the left side, you see all the various courses. Could be power electronics, could be drives, electric machines, and all these courses can be in different languages, as you can see here. Right now, of course, we work in English. The topic that we speak about right now is electric machines and drives, and of course, I told you this, we are working with a three-phase asynchronous machine. So a student will click on this topic here, so you can see that right now we are in the ILA course three-phase asynchronous machine. All our courses are made in exactly the same way. At the beginning, you will get your training contents and your prerequisites. Then you will have a little explanation about the equipment itself, what kind of panels and components you will need. Some explanations, technical explanations about the equipment that you're using. As you can see here, the servo machine test stand, the power supply, the multifunctional multimeter. Of course, very important, safety instructions. And then right now we come into the experiment about asynchronous motors. And here is the chapter, for example, connecting and starting, rotation, reversal, or load characteristics. I just click on the load characteristics. And the students, they get a full instruction how to follow the experiments step by step. At the beginning, you can see there's a little circuit diagram, how the setup is connected. And the same way, you see the circuit diagram, but with the real panels. They see how to mount the panels into the frame. And here down there with the buttons, you can click, for example, how to make the connection for the grounding, how to make the connection for the temperature sensor, the PC connection, only the motor circuit, and of course the complete wiring. Okay, now the student reads through the experiments, he gets all his instructions what to do. And you see here some empty placeholders in order to get your characteristics. For example, here in a star connection. But how to record the characteristics? For this, we use a different software, which is called Active Servo. You can activate your Active Servo in the right upper corner here. I'm going to switch to the Active Servo. This Active Servo software is specially designed to take all characteristics of various machines and also load experiments. On the left side, there is a display bar. I can double click into that display bar and I can simultaneously display 11 different values, which is speed, torque, mechanical power, slip, voltage, current, apparent power, active power, reactive power, power factor, and efficiency. Now you see here on the left side these 11 values which are displayed simultaneously and in real life. And now here in the chart you can see that I can also define which values to display in the axis. I can define the scale of each value. I can change the color of my grid, of the zero lines, different sizes and line width of the markers. I can change the font and the nominal values. Okay, so as well here I can type in my data from the machine which the student have to read on the plate of the machine. I can define the circuit, for example, whether I work in a phase and line with phase and line variables in a single phase circuit in AC or a single phase circuit in DC. I can define my ranges, my slope, so I can even, let's say, type in a specific starting point, or I can set up a table where I want to record my values. And of course, this is for safety reasons. I can set some kind of limits, like a lower speed limit, an upper speed limit, or a maximum torque. Okay, now I'm going to show you how we can record the typical characteristics of a three-phase asynchronous machine. For that, first of all, of course, I have to run the machine. I start the machine. And now, with this run button, I can activate my dynamic servo machine test stand. And you see here that the system tells me that I have to press the run button. This is made purposely that students realize that they are activating the system right now. This is also some kind of a safety feature. So I press the run button on the hardware. Okay. And now, similar to the manual mode, the servo machine test stand synchronizes to exactly the same speed of the motor, which you can see here on the left side in the display bar. And with this button I can start the ramp in order to record the characteristics. Okay, so I will stop the measurement, I will switch off the machine. Okay, so as you see here now, I see the typical characteristics. The orange curve here is the typical characteristic of a three-phase asynchronous motor. In addition to that, you see the cosinus phi and the current. Of course, I could also display here all the other values, which you can see on the left side, but then the picture would be a little bit overwhelming. Yeah. Okay. After recording the characteristics of the motor, I can easily press the right mouse button and copy this picture. Then I go back into my EILA course, into the placeholder, paste it, and then this value is stored into the student data. That means all the measurements, all the recordings that students do with this system are stored into their file. This file can be either exported as a PDF, for example, as a paper handout. It can be stored on a local PC or tablet, or it can be stored on the server of the school. The advantage is that also the teacher can go into the student file and see what he did. Okay, now I go back to my software active servo. I will clean up the picture in order to take a new characteristic. But this time I'm going to change the chart into a 4-quadrant display. Okay, now I'm going to change my presets because I would like to run the motor over several quadrants. That means I will change my starting point from 1500 RPM to 1600 RPM. As we are here in Europe, the synchronous speed is almost 1500 RPM. So when I change this to 1600, that means that the servo machine test stand will actually drive the motor. Then the endpoint will be minus 1000. That means that the servo machine test stand will change the rotation of the motor from clockwise to counterclockwise. Okay, so first of all I have to start the motor. Then I will press the run button. That means I synchronize the brake to the motor. And now I'm going to start the ramp. The system warns me, which is also a safety feature, it warns me that it will actually change the rotation and ask me whether this is correct. I say yes. Okay, now I will stop my recording. I will switch off the machine. So as you can see, obviously the current is out of our range, so I can easily also double click here and say adjust scale. So the scale will adjust it automatically by the software. Now I'm going to show you, if I press this button, which is called characteristics, I can select my first recording, and then you see this black sidebar here, and I can jump between the measuring points, and you can look after each value of the measuring points on the left side in the display bar. So that means it's easy to examine all these measuring points. As well, I can export all my data as the chart as a picture. I can export the chart as a bitmap, or I can export all the values as text. That means with all these data that you record, you can use them to process them in other software. Okay, so I'm going to change from the 4-quadrant view to the regular view, the 1-quadrant view. And now I change from the classic characteristics recording, I will change to the load characteristics. This is one specific feature of the dynamic servo machine test stand, that we can actually simulate or emulate different kinds of typical industrial loads. We say we bring the real world, that means the real industry, into the laboratory. In order to do that, I will change here from motor characteristics to load simulation. So, in the load simulation, I can simulate, for example, a pump, a colander, a hose drive, a compressor, a winding machine, an inertia wheel, or even a time-dependent load. I will start first with the pump. Okay, I will start again the motor. Press the run button. Okay. And now you see already down here, you see the working point. So if I change the load of this pump, you will see that the working point follows the motor characteristics. And I can use the camera here, for example, to record this working point at this specific position. So I took one working point, I changed my load again, I capture another working point, change the load again, I capture another working point. Okay, now I will stop this. I will also stop the machine. Now you can see, if I click on that working point, on the left side you can exactly see all the values recorded at this working point, at this specific working point. I can even display these working points if I press here on Add Labels. So that means the students can exactly see for each working point all the recorded values. Okay, so I will clean my picture here right now. I'm going to change my load right now, for example, to the time-dependent load. The beauty of the time-dependent load is that I can actually set my own torque diagram. I will capture, for example, this value here, and I can change this to here and here. So you see, this is my own torque diagram. I press the transfer button, so this torque diagram will be transferred into the control unit of the servo brake. So I move this down. Then I will start my motor again. I press the run button. And now you see that the brake or the servo machine test stand follow exactly this torque diagram. This is an arbitrary torque diagram which the student can define by himself. But still here right now I'm in the RPM mode. That means I measure my torque over the speed. I will stop this right now. So I can also change to a time diagram. So now I'm recording the torque not over the speed but over the time. And I can say, for example, record for 20 seconds. I press my start button again. I press run. And then here I start my recording. And here you can actually see that really the dynamic servo machine test stand follows the torque diagram that I defined before. Okay, now I change the load from the time-dependent load to an inertia wheel. I set the time to 1 second. I switch off the checkbox of RMS and I set the trigger to the speed. I move the trigger point a little bit on the timeline to the right in order to see the value before the trigger point. Now I'm going to start my recording already before I switch on the machine. Okay, so then I press the record button and then I start the motor. Okay, so I switch off this experiment right now. What you can see here is actually the dynamic response of the current. That means we are able to show the values not only with RMS but also the actual value of the current, voltages, etc. Okay, now you saw how to work with our dynamic machine servo test stand. You saw the different safety features. You saw how to work in the manual mode with the different kind of operation modes, the torque mode, the speed mode, and you saw the PC mode, the different load options in the PC mode, how to take characteristics, how to work with our software, with our curriculum, with our EILA courses. EILA is Interactive Lab Assistant. And now I'm going to switch to the power electronics part. For all the experiments before, we just connected the machine directly to the line power. Now I will connect the motor to a frequency converter. In order to do that, I change the connection. I connect the motor to the frequency converter. Okay, to the output of the frequency converter. Of course, I have to source the frequency converter. I have to feed the frequency converter with line power. Okay. So, okay, that's the connection. As you see here, the frequency converter is fed by the line power and the motor is fed by the frequency converter. I switch on the line power, I switch on the frequency converter. We use this panel, which is a self-commutated power converter. We use it for power electronics experiments as well as an educational frequency converter. As you see here, it has 6 IGBTs. Why do we use it also for a frequency converter, not only for power electronics? Because an industrial frequency converter cannot measure and display all values from current and voltages at the same time, which we can do here with this educational frequency converter. But you will see that later when I use the panel with the software. Right now I'm going to use this panel only in the manual mode again. So I can change here the mode. There are various operation modes. There's a DC mode, there's an AC mode, there's a DC mode, the AC mode, a three-phase mode. Yeah? I go into the three-phase mode, and then I can pick between different modulation mode. One is sine, vector sine, space vector linear, and space vector sine. So in this case I pick the space vector sine. Okay, then I just can press start, and you see on the LEDs that the unit is working, and then I can start my motor. Here you can see the frequency. Yeah? So in this way I can drive my motor with this educational frequency converter to whatever speed I want. Yeah? If I go down to a lower speed, the student can actually a little bit see how these IGBTs work as a valve. But this, I will show you this later on with the real power electronics experiments. Okay, I stop this here. Okay, now we run in the PC mode. Also for this topic we have an ILA course, Interactive Lab Assistant. We are in the chapter of power electronics, and within power electronics we are in the chapter of frequency converter drives. Also this ILA course gives the student a lot of information about the equipment itself, about different frequency converter applications, different design of converters, different types of converters, like a direct converter, a current source DC link converter, or voltage source converter. Yeah. You can see the design of modern frequency converters, the line power rectification. Yeah. Also you see a lot of nice little animation, how the rectification is working. Yeah. You see single phase, you see a single phase power supply, a three-phase power supply. Then we have a chapter for a DC link with a charge circuit for capacitors. But I'm going to show you right now a little bit here. I'm in the chapter of design for modern frequency converters. In order to run the motor, we have to use a so-called virtual instrument. Virtual instrumentation does not mean that we simulate what we're doing here, but we actually run the motor just with the software. I switch on the frequency converter. So this is the virtual instrument for the frequency converter at the moment. As you can see here, I have similar options to the manual mode. That means I have my modulation modes that I can change. I can show the chart for 1 period or 2, 3 or 4 periods. I can change the clock frequency, and I'm just going to press power here. As you hear, the motor starts. I can change the frequency, for example, to 60 Hertz. What you see here right now in the timing chart are just the fundamental components. The fundamental components are relevant for the motor. I'm going to double click into the chart because I would like to switch off the fundamental components for the voltage, and I'm going to switch off the fundamental component for the currents. But I will look to the real values of the voltage and the current. Okay, what you see now are the 3 currents plus the PWM voltage signal. If I change now between the different modes, you can easily see, or your students can easily see, how these signals change. For example, this is the block mode. You can also hear the difference. That's the sine mode. That's the vector sine mode. The space vector linear mode. and the space vector sine mode. Also, I can change the clock frequency from 1000 Hz, 4000 Hz or 8000 Hz. Yeah? Below here you see that we have the timing chart, we have voltage frequency characteristics, and we can see the voltage spectrum, and we can see the current spectrum. Yeah? And for example, if I change the different modes, you can see what happens with the spectrum, that you will have way more harmonics depending on the modulation mode. And obviously the aim is to have the maximum power with the minimum of harmonics. Okay, so now you saw how to work with an educational frequency converter. Of course, we are in the topic of drive technology. Before we were in the topic of electric machines. You can also use now the dynamic servo machine test stand in combination with the motor and in combination with the frequency converter in order to record various characteristics of the motor. But that is pure drive technology. But in order to understand drive technology, we have to learn before about power electronics. Because you know, on one side you have power electronics, then you have electric machines, and if you combine both together, it becomes drive technology. This educational frequency converter can also be used in order to teach the topics of power electronics for self-commutated power circuits, power converter circuits, and that's the next presentation. Okay, now we switch to the topic of power electronics. In this case, self-commutated power converters. For that we use our panel, self-commutated power converter circuits. The panel is fed by a three-phase isolating transformer, and the output goes to an intelligent power electronics load. In this case, we have only resistive loads connected. The panel itself has 6 built-in IGBTs with a freewheeling diode. That means the current can run through backwards. Yeah? IGBTs are slower than MOSFETs, but they have much higher proof voltage. Okay, in order to use this setup, we also use the PC. As you can see, the module runs in the PC mode at the moment. And I'm in our ILA course for self-commutated converters right now. It's pretty much the same with all the other ILA courses. That means the student get explanations about the training contents, about the prerequisites, about the equipment. Then we have a chapter for 1-quadrant converters and the chapter for 4-quadrant converters. So I'm go into the chapter for 4-quadrant converters. Yeah? Operation with a resistive load. Yeah? Again, first of all, you see the circuit diagram. That's the way how I connected it already. And of course we have again the assembly instructions. Yeah? The equipment itself, you see these 3 panels like in reality, the PC mode, the input and the load, and the complete wiring. Yeah? In order to start the experiments, I will work again with virtual instrumentation. Right now I use the 4-quadrant converter. I press the power button. And now I can change here my pulse width, that means the duty cycle. If I increase the duty cycle, yeah, you will see the output voltage and the output current. On the panel itself, you see that the LEDs are green. That means we have positive voltages and currents. I can go in the opposite direction. And now you see also on the panel that the LEDs are red. That means we have negative voltage and current. Yeah? So, right now I'm in the timing chart, and I use this instrument in the manual mode. I can, for example, also show the power vectors. So I will change again a little bit the duty cycle. Okay. So what you see here, you can see the power vectors. You see actually the apparent power, the active power and the reactive power. And you might wonder why there is a little bit of reactive power. The reason is that the resistors that we are using are wound resistors. So there is a little bit of an inductivity. That's the reason why there's a little bit of reactive power. Yeah. I can also change from the manual mode into an automatic mode. And with the automatic mode, I can record my control characteristics. If I press power, the system records the characteristics in an automatic way. Now I will change from the operation with a resistive load into the operation with a resistive and inductive load. Yeah. Again, you see the circuit diagram and the assembly instructions. I click on the complete wiring. You can see how easy it is to change the wiring, but still we are in the DC mode right now, no AC. This will come later. So I change my wiring. I will connect. Let me see. Okay. Now we have a resistive and inductive load connected to the system. Now I go into instruments again and I open the 4-quadrant converter. I press power. And now the students can already see the difference between a pure resistive load and a resistive and inductive load, because you see the smoothing of the inductivity, and depending on the clock frequency, the smoothing is higher or lower. Right now we have 1000 Hertz clock frequency. If I switch to 4000 or to 8000, you see that the smoothing gets higher. Yeah? This is called the E function of an inductivity. If I change to the power vectors here, you can see easily that there's a higher, way higher reactive power component. Okay, so I stop here. So far everything was DC, now we change to AC. In order to do that, I change my experiment. Yeah. I have the same connection, yeah, but I will get the instrument which is called AC converter. Okay, that's the virtual instrument for AC converter. I switch on power, yeah, and I double click into the chart and I will remove the fundamental component for the current and for the voltage. Now you see only the output voltage and the output current at the load. If I change my frequency, I go down to 1 Hertz, for example. You already see on the real hardware that the frequency changes, and the LEDs are still orange. That means it's a combination between green and red in this case. And if I go to 1 Hertz, the student can easily see how the valves switch between positive and negative. I go back to 60 Hertz. Okay, now I'm back to 60 Hertz. But we are still in the modulation mode, block modulation. Yeah. So I change now to the sine modulation. So you see already that the current is more shaped like a sine. And the higher the clock frequency, you can see more smoothing. Okay, you see what change if I change the clock frequency, you see that the current becomes a nicer sine wave because of the inductivity. Yeah. I can also show here, of course, again the voltage spectrum and the current spectrum, and again if I have the sine modulation with a higher clock frequency, I have less harmonics. Now we will change from the AC mode to a three-phase mode. For that I pick the experiment three-phase inverter. Here I pick the operation with block commutation. Again, you see the circuit diagram and the wiring. So I click on complete wiring. I change my wiring here. So I have this one here and this one here, and I need the third cable because I'm in a three-phase operation right now. So now I'm in the three-phase operation with inductivities and resistors. You see down here is the start point. I will pick the instrument three-phase converter and I press power. Now you see the timing chart. In the timing chart I switch off the fundamental components and I switch on 1 voltage and the currents. Okay. I can also change here to the modulation chart. And then you can show your students the different types of modulation. For example, right now that's the block modulation, that's the sine modulation, the vector sine modulation, the space vector linear modulation, and the space vector sine modulation. Okay, now I would like to speak about space vectors. We stay in the same experiment with a three-phase inverter, but I open the instrument space vector control. Okay, I press power and I'm in the base modulation mode. In this modulation mode, if I change the angle, the space vector just jumps within the hexagon for 60 degrees. Every jump is 60 degrees. Okay, and you can also see on the real hardware, you see the switching between the three legs of the IGBT. You can see the same thing also at the load. As you can see, the color of the LEDs changes. Okay, so now I change the modulation to a linear modulation. Right now what is happening, we add additional neighboring base vectors, but still the vector runs within the hexagon. You see the same thing at the IGBT and at the load. And the third mode is the sine mode, and now we are also using neighboring vectors, but the result is that the vector runs within the circle. And this is what we would like to have in reality, for example, to drive a machine, in order to avoid too many harmonics, that the motor runs in the perfect and most economical way. Okay, so far I demonstrated everything. I demonstrated the space vector control only with the inductive and resistive load. I'm going to change now to a real motor. In order to do that, I have to change my connection. I will disconnect the panel here, the load, and I will connect the real three-phase asynchronous squirrel cage motor. Okay. Okay, so I switch on the power again. I'm in the mode base, I'm in the base mode. So, and if I change the angle, you will see that also the motor jumps the steps of 60 degrees. I have to reduce the voltage a little bit, otherwise there's too much power, too much voltage and too much power on the motor. So If I change to sinus, you will see that the motor runs within the circle and can be controlled smoothly. And that's actually the reason or the idea of power electronics, to run the motor in the most economical way with less harmonics. Now you see how you can work with the self-commutated power converter circuits. We use different operation modes. We work with DC, AC and three-phase, and also you saw that we cover the entire topics of space vector control. I hope you liked it, and thank you for your attention. See you next time.